All right, so this part, it can either be really easy or you have to remember a couple tricks for it. So this one is evaluating limits analytically. So what we were just doing was evaluating limits graphically, so just being able to look at a picture and evaluate what the limit would be. This is evaluating limits analytically, so you're actually given an equation and you have to figure out what's the limit as x approaches such and such. So sometimes it can be really easy, and it was funny because I remember when you guys were taking the test on limits back in chapter 1, some of them you just substitute the number in. So you literally just take the number and plug it in and figure out what it equals, and you guys were freaking out about the parts when it's not that you just assumed. By the time we got to the test, you're like, we can never do that. So a bunch of people got those questions wrong just because they didn't even try to substitute the number in. So the first thing you should always do, whenever it says to evaluate a limit, like what's the limit as x approaches of this function, the first thing you should always do is try to substitute the number in to figure out if it's an easy limit to integrate. So at this point in your mathematics career, we can skip over that first part. Remember how I said Peterson's pretty sarcastic and long-winded? So he gives a lot of examples and explanations. So if you like that, this is a good review book to get, Peterson's. So if we keep going, here we go. Instead, you need to learn the three major methods of finding limits. So here are the three major methods of finding limits. The first one is substitution, like I just said, and that's the first one you should always try. The second one is to factor. See if you can factor something on the top and bottom and cancel. Because remember how if there's a hole, you're going to have the same factor on top and bottom. So if you can get rid of that hole, it'll give you the same limit. So that'll be good. So factoring after substitution, and then the last one is the conjugate method. So if there's like a square root in the bottom or the top, you can multiply by the conjugate of that. So like 1 plus the square root of x, multiply by the conjugate of that. It'll usually get rid of that square root to help you simplify a little bit. So again, remember that limits answer this question. Limits answer the question, where is the function heading? Does it have to get there? No, it doesn't have to get there. So if there's a hole in the graph, that's okay. Just where is it heading? Where is it going to? So a lot of times it actually does reach that value, so it actually will equal the value that it's heading to, but sometimes it doesn't have to. So we'll use the substitution method first to try and see if it works. All right. Example. Remember, first one, substitution method. So just take x equals 2 and plug it into that function everywhere you see an x and see if it equals something nice and pretty. All right, drum roll. 2 squared minus 4 times 2 plus 9 is?
5.
5, good. So literally sometimes, now I'm not saying that your entire AP test is going to be filled with questions like this, because obviously it would be too easy to pass. But could there possibly be a question that's like as easy as just take the number and substitute it in? Yeah. And it will probably look a lot like this. Maybe not the same equation or whatever, but it'll just be like a simple, like the limit as x approaches blank of this function. First thing you should always do, substitute that number in. It won't always work, but sometimes it might, and it'll be a really easy question for you. It'll take you 5 seconds. All right, let's try another one. Try this one. It's a little bit more difficult if you're not familiar with trig functions. So we'll write it out. Trig's great.
Matt's feelings.
Don't hurt Matt's feelings. It hurts my feelings all the time. Okay.
Oh, it's time.
Yeah, it's times. Are you eating a brownie, Lloyd?
Yeah.
Oh my god, it's like 9 o'clock in the morning.
I don't know why you did that.
Oh, that's
Although I did bring donuts, I can't really speak. It's only just as much sugar as a brownie.
Well, you have boba.
That's so true. It looks good.
I made brownies. It's alright.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 1 Is it working?
Yeah.
I'm going to do my very best, by the way, to not do these problems for you guys, to let you do them. So if you ever feel like I'm doing too much, just let me know. Well, during class, I like to help you guys out with the notes since we're on a time crunch. But since this is your review session, not mine, I'll go at your pace.
I'm struggling with the easiest myself.
Which one's this? Partial fraction?
Yeah. I just had a set of equations so I can get rid of stuff.
This one? Or down here?
I'm doing this one.
You're good on this one, though, right?
Yeah. Did I set it up right?
Mm-mm.
No?
Well, hold on. You only have to do this when it's a quadratic factor, right? Or do you do it when it's I thought you only did this when it's the quadratic one. You do something when it is I thought you just put another C over that. Yeah, but if they're linear together. The repeated linear factors aren't the same as the quadratic ones. Here, look here. Repeated linear factors. Look, you just do A over X plus B over X plus 1 plus C over X plus 1 squared.
Okay.
That's all.
Yeah.
Oh.
All right, back there, you guys got an answer? Good. So, cotangent to 3 pi over 2 is down here, right? This is 3 pi over 2.
Yeah.
Cotangent would be cosine over sine. So this is the point -1 comma 0. Oh, actually, I lied.
Are you? Yeah, 0.
Thank you. So cosine over sine would be 0 over -1. So that one's 0. So anything times 0 is just 0. So this one goes to 0. So again, substitution, easiest method. This one we can do in our heads really quick, so let's just do this one in our heads.
Intractor.
I
mean, like a.
We are going to. Yeah. That's what you said, right?
Yeah.
Yeah. Because if you look quickly in your head, on the top you could plug in -1 just fine. But if you plug in -1 to the bottom, what happens?
It makes it into 0 and you can't.
Good, it goes to 0. We can't have that. So if you look at the top, actually, plugging in -1 to the top would be 1 plus 3 minus 4, which is also 0. Do you guys remember what that's called when you get 0 over 0?
Undefined.
Starts with an I. All right, when we multiply by the conjugate, we get the square root of x minus 3 minus 2 times the square root of x minus 3 plus 2 over x minus 7 times square root of x minus 3 plus 2. So on the top, x minus 3 squared x minus 3 gives you x minus 3. And then minus 4. On the bottom, you get x minus 7 times the square root of x minus 3 plus 2. So on the top, you get x minus 7. On the bottom, you get x minus 7. Those cancel. So this is 1 over the square root of x minus 3 plus 2. If you take the limit as it goes to 7, if you plug in 7 into the bottom now, you get 1 over the square root of 7 minus 3, which is 4 plus 2. So that's 1 over 2 plus 2, which is 1/4. Good. Gotcha. That's your key right there. A lot of times, by the way, they're not going to give you one on the non-calculator section of the AP exam. So if you're taking this on the non-calculator section of the AP exam, they would never give you one that didn't happen like that, right? So they're not going to all of a sudden trick you. So go back and keep checking your work and like know in your mind that this should work. If this doesn't work, then there's no way you can evaluate that limit easily without using L'Hopital's rule, which is I'm going to right now. Actually, I'm going to show you guys how easy it is. Now that you guys know how to take derivatives, yeah. So definitely do it this way, obviously. So there's this rule called L'Hopital's rule, which you technically shouldn't have to learn until Calculus BC, but it's a super easy rule, and it actually helps you a lot with problems like this. Here's the reason why. When you get the indeterminate form, so if you plug something in, you get the indeterminate form, there's this rule called L'Hopital's rule that says that if you would like to, hint, hint, probably do it, if you would like to, it works out that you can actually take, and this is only when it gives you the indeterminate form, so only when you get 0 over 0 or infinity over infinity. You can do the L'Hopital's rule, which is taking the derivative of the top taking the derivative of the bottom, and then try plugging in 7 again. So what's the derivative of the top?
1/2.
That would be the combination of the derivative and the integral. Good. To the negative 1/2, what's the derivative of the bottom? 1. If you plug in 7 again, you get 1/2 times 7 minus 3 to the negative 1/2, which would be 1/2 times 4 to the negative 1/2, which is 1/2 times 1 over the square root of 4, which is 1/2 times 1/2, which is 1/4. Yeah, that's called L'Hopital's rule. So L'Hopital's rule says, so I can repeat, if you have the indeterminate form, so if you try to use direct substitution and you get 0 over 0 or infinity over infinity, you can use L'Hopital's rule. If you ever see it written out, it actually looks like L''hospital. Some people spell that word differently, but some people put the S, some people don't, but the way that I learned it was with the S. So it looks like L''hospital, but it's L'Hopital. So indeterminate form, 0 over 0, infinity over infinity. You could take the derivative of the top, derivative of the bottom, and then plug in whatever the x value is one more time, and it'll give you the same answer as doing what you just previously learned. Now, the reason we don't teach you that when you first learn about limits is because you don't know how to take derivatives yet. So obviously you wouldn't know how to do L'Hopital's rule if you don't know how to take derivatives. But obviously this one's much easier. You don't have to do conjugates. You don't have to worry about all that. Easy peasy. What are you looking at?
Have you noticed it? Like this part of the ceiling is going in.
Oh, really? I didn't notice that. It's probably the wind. All right. So I'm going to give you guys some problems again to do on your own. We'll check our answers in just a minute, but go ahead and try these 4. It says don't use the calculator in problems 1 through 6. When we get to number 7, you guys can use a calculator. All right. So for L'Hopital's rule, we plug in 9 to the top, and you get 3 minus 3, which is 0. You plug in 9 to the bottom, you get 9 minus 9, which is 0. So this is the indeterminate form, 0 over 0. So if I take the derivative of the top, the derivative of the square root of x is 1/2 x to the negative 1/2. And the derivative of the bottom, which is 9 minus x, would be negative 1. So this is 1/2 times 9 to the negative 1/2 divided by negative 1. Which is 1/2 times 1 over the square root of 9, which is 3, divided by negative 1, which is negative 1/6. Again, that's using L'Hopital's rule. Are you sure you don't want me to show you the other method using the conjugate rule? I can, yeah. If you don't want to, keep working on numbers 3 and 4. If you do want me to put it up there, I'll do it right now. Because like I said, it's good to know both just so that if you forget on the test, you're like, oh my god, I don't remember L'Hopital's rule, let me just do the other way. So you have to multiply by the conjugate, and the conjugate's always the conjugate of the one with the square root. So the conjugate of x minus, the square root of x minus 3 is the square root of x plus 3 over the square root of x plus 3. Hi.
What's up?
Welcome, guys.
Good morning.
If anybody, Asma, or you guys, if you want a donut, there's donuts right here. If not, take a seat. Sorry, La Jolla, you too, I forgot. As people have been coming in, I have been telling them. You can have one if you want. All right, so when I multiply on the top, the square root of 3 minus 3 times 3, which is 9. I'm sorry, that's the square root of x minus 9, huh? Oh, square root of x times the square root of x is x minus 9. There we go. Divided by 9 minus x times the square root of 3, square root of x plus 3. Do you guys remember what happens when you have x minus 9 and 9 minus x? Good, they cancel to a negative 1. So that would equal negative 1 over the square root of x plus 3. So when you plug in 9 to that, Farah, you get negative 1 over the square root of 9 plus 3. So that would be the square root of 9 is 3 plus 3. So that would be negative 1 over 6. So both ways work, just to give you that information. I'll put them all on YouTube, yeah. Hello, what's up? You here for STEP? Oh, hi.
49ers out.
She said, get out.
Packers fans. That was a hard loss. already still kind of stings.
So those of you guys who are just trickling in, just to give you guys a brief overview, all the stuff that we're doing right now, I'm going to put online, so I've been taking videos of it, so if you want to know what you missed in the first hour, you can just look online for that. At the very beginning, we talked about, those of you who are still working, is anybody still working on 3 and 4? Let's put those answers up to them, just so that we can go ahead and I'll tell you guys what I was going to say in just a minute. All right, so for number 3, the answer is... For number 3, the answer is -3. For number 4, the answer is 12. Are we good on those?
Whoa.
Which one?
Oh. Just kidding.
All right. Just really quick, just because a few people just trickled in and I want them to know about L'Hopital's rule so they don't forget, or so that they can learn it as well. For those of you guys who just trickled in and don't know about L'Hopital's rule is a rule that you actually aren't supposed to learn until Calculus BC, but it's really easy and it's really helpful for limits. Because remember how sometimes you can use direct substitution. So we learned that there's 3 ways you should do limits. Try substitution first. So for example, in number 3, substitution works pretty well. You just plug in 1 to everything and you get -3. So first try substitution. If substitution doesn't work, you can try factoring and canceling out common factors because there was a hole in the graph. Or you can try multiplying like the conjugate, like we did on number 2, multiplying by the conjugate. But I was telling everybody else before you guys got here that there's an easier way to do limits. If you plug in by substitution, so for example for number 4, when I plug in -2 to the bottom, I get 0. When I plug in -2 to the top, I get 0. If that happens, that's called the what, guys?
The
Indeterminate form. So if I get 0 over 0 or infinity over infinity, that's called the indeterminate form. And I can use a rule called L'Hopital's rule, and it only works if you get the indeterminate form. So it only works with 0 over 0 or infinity over infinity. But L'Hopital's rule says essentially that you can take the derivative of the top and the derivative of the bottom, and then try plugging in the limit one more time. So what's the derivative of x cubed plus 8?
2x squared plus
3x squared.
3x squared. Yeah, 3x squared, sorry.
And what's the derivative of the bottom? X plus 2.
1.
1. And if you plug in the -2 one more time from the limit, if you plug in -2 into that, you get 3 times -2 squared, which is 3 times 4, which is 12. L'Hopital's rule? It looks like an L apostrophe and then the word hospital. It looks like that. It's a French word, French name, I should say. But L'Hopital's rule. It's a really easy rule. They don't teach it in Calculus AB. They're going to in future years. They're adding it to the AB curriculum. But it's a super easy rule. It doesn't take a lot of brain power. And it's really good for limits because if you didn't do it this way, you'd have to factor out the top, factor out the bottom, cancel a common factor, and then use direct substitution. So this way is just much easier. Keep in mind it only works when you have the indeterminate form. So don't try it always. You have to make sure it equals 0 over 0 first.
For factoring cubes, a squared minus h.
This one would have been a plus b, so x plus 2, times a squared, so x squared, minus ab, so minus 2x, plus b squared, so plus 4.
Okay.
And then all over x plus 2. This one cancels with this one. If you plug in -2 that way, you can still evaluate it that way, but this way you just need to know more information. L'Hopital's rule just makes it super easy and super quick. All right, good. Try these 3. Number 7 you can use a calculator for, remember. So number 5 and 6, no calculator. Number 7 is calculator okay. You guys what this graph actually looks like? X squared minus the square root of 5 over 5 minus x. Looks like this. Yeah? It's a really good program.
That's great, because when I don't know graph,
What was it? 5 minus x?
yeah.
Alright, that's what it looks like, except at x equals 4. So at x equals 4, it equals 0. So at 4 comma 0. So if there was a hole in the graph, I don't have a hole in my graph because I didn't put one there. I probably could though. I don't know how to do not equals. X, do you see a not equals button? I don't either.
Nice.
So I don't know how to do x not equal to 4, but you get the point. So if there was a hole over here at x equals 4, it would look like this. So it's going towards 16 minus the square root of 5, which is this value right here. Except at this point it equals 0, but over here the limit is going to 16 minus the square root of 5. Are we all okay with that piece? So piecewise functions. Don't get confused with what it actually equals. Be only concerned with what it's going to. The limit is always what it's going to.
It's irrelevant, but why is it not defined in x equals 4?
Because the piecewise functions, you can tell it whatever you want. Piecewise functions don't have to be like, they're just saying, here's your function, but it's not defined at x equals 4. Instead, at x equals 4, it equals 0. Just because they wanted to. This question was literally designed just so that they're testing whether or not you know the definition of the limit.
It's gonna be 1, right?
Say it again?
Just kidding.
You can't use that rule.
No, I'm not talking about 6. I'm talking about
Did you guys get an answer for 6 yet?
-1.
For 6?
Yeah.
Not quite.
Wait.
Okay, would you have to graph it? Do you graph that?
Well, you don't have to graph it, but you should know what the graph of it looks like.
It's like
The graph of it looks like this. Well, first of all, whenever you have absolute value, you have to split it up around where it would equal 0.
Yeah.
So the absolute value of x gets split up around 0 because that's what splits up the negatives versus the positives, right? If it was x minus 2, it would get split up around 2 because that's what determines the negatives versus positives. So this you could split into a piecewise function and say that it's positive x over x when x is greater than 0, and it's negative x over x when x is less than 0. Remember how we were doing that with the absolute value functions, making it the negative version wherever it was negative, so that it would flip it above the x-axis? So x over x is just 1. So it's 1 when x is greater than 0, and it's negative 1 when x is less than 0. So the function actually looks like this. So as it approaches 0, what's the limit here? Doesn't exist. Good, it doesn't exist. So as it's approaching from the left-hand side, it equals -1. As it's approaching from the right-hand side, it equals +1. But at 0, because the left and right-hand limits aren't equal to each other, it doesn't exist.
Sorry.
That's okay?
For absolute value ones, is it always going to be, does not exist because you always have to split it up?
It depends. If this said what's the absolute value of x approaches 1, 1. But the only reason it gives you a problem with 0 is because that's where it gets split. So it's not that the absolute value makes it does not exist, it's that the x is approaching the value that makes it not exist. Yeah. Did you guys graph number 7 in a graphing calculator? Because that's the one where you can use a calculator. I'll graph it on my computer just so we can see it together. It's the limit as x approaches 0 of x sine of 1 over x. Looks kind of like that. Yeah.
It's oscillating, does not exist.
Good. It starts oscillating. But if you zoom in far enough, does it eventually go to something?
Whoa!
You're right.
It's like a corridor.
It looked like it did, but it just keeps oscillating back and forth. No matter how far I zoom in, it's just going to keep oscillating back and
Yeah,
forth.
it looks like a hallway.
So yeah, this one doesn't, I don't believe it exists. It looks like it's going towards 0, but it just keeps oscillating back and forth.
It goes on forever. Where's the door to the back? All the way at the end.
It's like that and with my own mansion.
Oh, yeah.
This one actually says that the limit is 0.
What?
Yeah, because like you plug in the 0 at the bottom and you get 0 and then 0. It's just 0 times.
Kind of. It's not 0 over 0 though, because 1 over 0 makes it undefined. So it's 0 times sine of undefined values. So the reason that this one would actually equal 0, even though it is oscillating, is because notice how it's oscillating in a fashion that gets confined to such a small area that it's oscillating around one point. So it's not oscillating like this, like the sine function would, right? The reason that we said it wouldn't exist when it was oscillating is because they imagine oscillating as being big oscillation. So like between this number, this number, this number, this number. But this one's oscillating in like almost like a pyramid fashion that it narrows it down to one number. So it's going to keep oscillating, you're right, the more you zoom in, but it's going to be oscillating at 0. So the fact that it gets down to one number is why that one's okay. I know that's probably a little confusing.
Yeah, the ones that didn't come.
That's right. So yeah, this last one down here is going to 0. It is oscillating the more you zoom into it, but it's oscillating at the point at 0. So that's why it would equal 0. All right, next.